Hello friends, so today we are going to solve some questions, and these questions were asked in the year 1988. We have two questions from the year 1991 and we have from the 1989, and finally we have here from the 1990. So total we are going to solve 5 previous years questions that was asked. So in this process, the first question, which was asked in the year 1991, and it says that a wire loop carrying a current I is placed in the xy plane as shown in the figure. If a particle with a charge q and mass m is placed at the center P and given a velocity v along np, see figure, find its instantaneous acceleration. In the part B, it is said that if an external uniform magnetic induction field B, which is equal to Bi iota rather, is applied, find the force and the torque acting on the loop due to this field. So we are given this figure. In this figure, we basically have an arc. This is not a complete circle. The major portion, it says that the current is flowing only between this arc. So this is the direction of the current which is flowing on the arc, and P is the center, and in this P a charge Q is given a velocity along NP, and the angle subtended by this, you can say, chord Mn at the center is 120 degree. So we can just, you can say, redraw this figure again, especially with respect to the arc as well as this triangle. And so we have our Mn and we have this arc, and we have a center P. Current is flowing in this direction. This is current I, as well as this will be current I, and center P, and the angle is given 120. So let us draw a perpendicular bisector which passes through this point P. So this angle will be about 60 degree. Similarly, this angle will be also 60 degree, and the charge is given a velocity along this side. So this is a plus q, and we are given that this is the axis which are representing. So within this axis x and y, this is our x-axis and y-axis. So we can represent the direction of the velocity. So this is our velocity, and we can say this will be a velocity of the charge q, and this will be making an angle of 60 degree with the horizontal. So we already know the formula for the magnetic field at the center of full circle loop. Based on that formula, we can derive the formula for this, you can say, half of the or part of the circle. We say that magnetic field at the center of full circular loop and circular loop having radius a, and carrying current I, and carrying current I. So we can write that the magnetic field for the circle will be equal to mu naught I upon 2A. But the current is being carried by this arc. Okay, so this arc is the only portion of this entire circle which is carrying the current. So we can find out the magnetic field due to the circular arc. Magnetic field due to circular arc, and we assume that the arc of the circle subtend the angle of theta at the center. Then then later on we can substitute theta as 120 degree. So we say arc subtends angle theta at the center. So we can say that the magnetic field contribution of this particular arc, of this circular arc, will be a fraction of the full circle. So we can say magnetic field contribution is proportional to fraction of full circle. So based on this, we can write that the magnetic field because of the arc will be equal to angle theta divided by total angle, which will be over 360, that is 2 pi, multiplied by magnetic field of the circle. And we know that the angle subtended by the arc at the center is 120. So our theta is our 120, which will be equal to 2 pi by 3. So we can find out theta upon 2 pi will be equal to 2 pi by 3 multiplied by 1 upon 2 pi, which gives us 1 by 3. So from here we can say P arc will be equal to 1 by 3 multiplied by magnetic field because of the circle, which is our mu naught I upon 2A. And we can further solve it. We can write the magnetic field due to the arc will be approximately equal to 0.16 mu naught I upon A. So this is the magnetic field of the arc at the center P. At the center P. And for the direction, we can easily see using the right hand rule that it will be along the outward from the plane of plane at the center P, or we can say that direction will be outward from the plane at the center P. Or in simplest term, we can say along positive z axis, or we can say positive k unit vector. Now we can also find out the magnetic field due to a finite straight wire, because this arc is this entire consisting of two parts. One is the arc and another one is of this straight wire. So we found out the magnetic field because of this arc. Now we are going to find out the magnetic field because of this straight wire. So we can say magnetic field due to finite straight wire. And straight wire at a perpendicular distance r. At a perpendicular distance r. So the formula is our B is equal to mu naught I upon 4 pi r, and here we have sine of theta 1 plus sine of theta 2. Here theta 1 and theta 2 are the angles subtended by the end points of the wire at the point P. So from here you can easily see that because of this is our straight wire. Let me draw it here only. So we have a straight wire Mn, and this is point P. So this is our perpendicular distance, which we are calling as r, and theta 1 are the angles subtended by the endpoints. So we can call this as our theta 1 and the other angle as theta 2. So we can specifically use for this Mn wire, and theta 1 and theta 2 is our 60 degree. So we substitute value. So theta 1 is our 60, theta 2 is also our 60, and the length of the wire, once again, yeah, it is given as A. So this distance is our A. So this will be also our A. Okay. So the perpendicular distance will be our R, which is our R by 2. A by 2. So R will be equal to A by 2. So we can just modify it. So magnetic field due to straight wire Mn will be equal to mu naught I is 4 pi A by 2, and we have the sine of 60 plus sine of 60, and we can further solve it. This 2 goes with 2, and we can write it as our magnetic field Mn will be equal to mu naught I upon 2 pi A. This becomes twice of sine 60, which is our root 3 divided by 2. and here also this 2 goes with 2, and we can say that the magnetic field because of the Mn will be equal to, this comes as root 3 mu naught I upon 2 pi a, and we can approximate it. We can say magnetic field because of this Mn will be approximately equal to 0.27 mu naught I upon a. So we found out the magnetic field because of the straight wire also, and the direction will be, you can see, into the plane. Direction will be into the plane, or we can say minus z axis. So this is at point P. At point P. Now at point P we have two magnetic fields. One is up the, you can say, outward, and that is positive z axis or positive k unit vector, and other one is the into the plane. So we have two fields and both are in opposite direction. So we can find out that net magnetic field at P net magnetic field at P, let us suppose that is given as B. So B will be equal to our B1 minus B2. Okay, because one is inward and other is outward. So we substitute values, and we can write that our B will be equal to 0.16 mu naught I upon A minus 0. Let me write it positive, and then we can use the sign, much more convenient. 0.7 mu naught I upon A, and this gives us equal to minus 0.11 mu naught I upon A. So this is our net magnetic field, and its direction will be into the plane because of the negative sign, into the plane, or we can say minus k unit vector. Now we come to the velocity part. Now this velocity, this is our x-axis and y-axis, and velocity is making an angle of 60 with the velocity of the charge, or we can say v is making an angle of 60 with the horizontal. So here we can, and this is moving along NP. So here we can divide into two components. We can say x as well as y. So velocity, or we can say particle velocity, charge velocity, v along NP we can write it as v is equal to v cos of 60 I unit vector plus v sine of 60 and j unit vector, and we can easily substitute the values. we are going to get this as, one second, let me change this part. Let me write it as capital V. So we can write this as V by 2 I unit vector plus root 3 by 2 V j unit vector, and this is our speed, and we found out the charge. Okay, and anything left? Yeah, we still need to find out the instantaneous acceleration. Okay. So here we can find out the force acting on it, and based on the force we are going to find out the acceleration on the charge. So now we say magnetic force calculation. Magnetic force, so let us call that Fm, will be equal to Q. We have here V cross net magnetic field, and B net is our in minus K direction. So we just calculate first of all the cross product. So we say V cross B net will be equal to I j K. We have V by 2 root 3 by 2 V and 0, and this comes as 0 0 minus 0.11 mu naught I upon A. And this is quite simple. You can just write the final part, and let me give the direct result for that. We get that our magnetic force will be equal to Q, and this will be minus 0.11 mu naught I upon A multiplied by root 3 by 2 V I unit vector plus 0.11 mu naught I upon A multiplied by V by 2, and here we have J unit vector, and we can easily take some factors common. So Fm will be equal to 0.11, and here we have mu naught I QV divided by 2A, and we get this as J minus 3 I unit vector. So this is the force because of the magnetic field. Now we can use the simple Newton's law, and that is going to give us a acceleration. So we can say acceleration A will be equal to Fm divided by mass m, and we already know Fm, which is our 0.11 mu naught I QV divided by 2am, and this comes as J unit vector square root of 3 and I unit vector. And we are supposed to find out the acceleration, and it has two components. Okay, so this is our instantaneous acceleration, and we can also say it has two components. It has two components. One be along x direction, and which will be our minus 0.11 root 3 mu naught I qv divided by 2am, and the other one will be our y direction. This gives us 0.11 mu naught I qv divided by 2am. Now we come to the part B, and part B, we have an external magnetic field which is applied in I direction. Okay. So we have to find out the force as well as torque acting on the loop in this particular field. So we come to the part B. So in this, it is placed in a uniform external magnetic field that is acting in I direction. Current loop is placed in external uniform magnetic field, which is given as B is equal to B I unit vector. So we can find out, first of all, what will be the net force acting because of this uniform external magnetic field. Okay. So the important thing is that the magnetic field, or we can say B, is uniform. Okay. And the force is given as a formula. A closed integral is of I cross B multiplied by dl. And here the force on each segment of the loop will be equal and opposite. Okay. From there also we can come to the conclusion that the net force will be equal to 0. So we can say force net will be equal to 0. So therefore no net force acts on the loop. And in the second part, we are supposed to find out what will be the torque. And the basic formula for the torque is our magnetic moment multiplied by the magnetic field. Okay. So first of all, we have to find out what will be the magnetic moment. And for magnetic moment, we should be knowing the area. Okay. So let us start with magnetic dipole moment of the loop. Magnetic dipole moment of loop denoted as capital M, which will equal to current, area, and its unit vector. And this K unit vector indicates that the dipole moment is perpendicular to the plane of the loop. Usually this K unit vector, it can be represented as n unit vector, and we can say that this n unit vector will be equal to K unit vector, and this indicates that dipole moment is perpendicular to the plane of the loop. To the plane of loop. Second, we are going to find out the area of the loop. Area of loop, which is given as A, and this area of the loop is consisting of two parts. In the first part, it has a circular arc, and this circular arc is making an angle of 2 pi by 3 at center. And the second, it is having a two line segments. Two line segments. So therefore, our area A will be equal to 1 by 3 pi a square minus 1/2, and this comes as 2a sine of 60 multiplied by a cos of 60. And this is simple trigonometric identity. We can just solve it, and we are going to get our area A will be equal to 1 by 3 pi a square minus root 3 by 4, and here we have a square. And we can just approximate it that our area is approximately equal to 0.61 a square. So magnetic moment, capital M, will be equal to 0.61 a square multiplied by current I, and then direction will be our k unit vector. Now we can find out the torque. Torque acting on the loop. Tau is our magnetic moment with magnetic field B. We already know all the value of magnetic moment as well as the magnetic field B. So we can say our torque, that is tau, is 0.61 I a square, and with a k unit vector, and B is our B but with respect to I unit vector. And we know that k unit vector cross I unit vector is our J unit vector. So therefore, torque is equal to 0.61 I a square B, and this comes as J unit vector. So these were the two things which was asked in this particular question. So we come to the next question, which was asked in the year 1990. And here it states that two long parallel wires carrying current 2.5 ampere and I ampere in the same direction directed into the plane of the paper are held at P and Q respectively, such that they are perpendicular to the plane of the paper. The points P and Q, located at a distance of 5 meter and 2 meter respectively, from a collinear point R. See figure. So based on this, we have two questions. First states that an electron moving with the speed of 4 into 10 to the power 5 meter per second along positive x direction experiences a force of magnitude 3.2 into 10 to the power minus 20 Newton at point R. Find the value of I. And the second, it says that find all the position at which a third long parallel wire carrying a current of magnitude 2.5 ampere may be placed so that the magnetic induction at R is 0. So in this case, we are given that we have two wires that are placed at point P and Q, and they are carrying current into the plane of the paper and perpendicular. And we have a third, we can say third collinear point, which is given as R. And the current through point P wire is 2.5 ampere and from Q is 1 ampere. And the distance of the respective P and Q with respect to this point R is given. So in the first case, we are supposed to find out that the value of the current I, and this current I is our, okay, I think this is I ampere, it should not be 1, might be, this should be I, okay, because here mentioned carrying current 2.5 ampere and I, same direction, are held at P and Q. Yeah, so I think this should be I. So first of all, we are interested that to find out this value of current I, and it says that we are given that electron with the velocity v positive experience of force of magnitude at point R. Okay, at point R there is an electron, and this electron is experiencing a force that is given as 3.2 into 10 to the power minus 20 Newton. So in this case, we are going to find out the magnetic field at R because of wire P, magnetic field at R because of Q. Then we are going to find out the net magnetic field, and then we are going to move forward. So we first start with magnetic field at R. At R, due to wire. So in the first case, we have wire P. Let us call that as magnetic field because of wire P, and that will be equal to our standard formula is our mu naught I, let us call that IP, and this is our 2R, and let us call this as RP. We substitute value, we get this as mu naught upon 2 pi, we have 2.5 and divided by 5. So this gives us the magnetic field because of point P at point R is our mu naught upon 2 pi multiplied by 0.5. Now we come to the wire Q. So magnetic field because of wire Q, we can write this as mu naught, and we have this current because of Q and 2 pi and distance of this point Q with respect to R. So we get this as mu naught upon 2 pi, current is given as I, and the distance is about 2. And the direction of the current is same in both the cases. You can say current is in same direction into the plane of paper, into the plane of paper. Therefore, net magnetic field at R. Net magnetic field at R, B at point R will be equal to magnetic field because of point P, magnetic field because of point Q. So we can say our magnetic field at R will be equal to mu naught upon 2 pi. This comes as 0.5 plus I by 2. And we can just solve it a little bit, and this will be giving us mu naught upon 2 pi I by 2, yeah, and this will be our I plus 1 divided by 2. 2 is the LCM, and this comes, yeah, and so we can say magnetic field at R will be equal to mu naught upon 2 pi, this comes 1 upon I divided by 2. And we are also given that the net force at point R. Net force at point R, and at point R, or we can say at point R, on the electron moving with velocity v, moving with velocity v in magnetic field B, and this will be our Fm is equal to BQV, and here we have sine of 90. We substitute the values, and this is given as 3.2 into 10 to the power minus 20, and magnetic field we just found out is mu naught upon 2 pi, and here we have I plus 1 divided by 2 multiplied by 1.6 into 10 to the power minus 19, and this is 4 into 10 to the power 5. And we can easily find out the value of the current. So current value will be equal to 4 amperes. And next part, it is asked that find all the position at which a third long wire parallel to carrying a current of magnitude same current 2.5 ampere, and that is of wire P. So the current of wire P and this third wire should be same, and it says that magnetic induction at point R should be equal to 0. So let us find out the position of third wire. Position of third wire. So we can say the total field at R total magnetic field at R due to P and Q we already found out the value of current I, so this becomes mu naught upon 2 pi, and this is our 4 plus 1, that is 5. And the third wire, it says that the net magnetic field at the point should be equal to 0. So it means the third wire should produce a field that it will be in opposite direction. Okay. So it says that net magnetic field at R is equal to 0. So therefore, the third wire should produce a field in opposite direction. In opposite direction, which basically means upwards. And we already know the formula. So we can say that our B is equal to mu naught upon 2 pi I upon R. And we substitute the value 10 is power minus 7 into 2.5 divided by R is equal to 5 into 10 is power minus 7. And if we solve, the value of R will be coming as 2.5 divided by 5, and this will be our, one second, there is some, yeah, I wrote, you can say this is our mu naught upon 2 pi multiplied by 5 is equal to mu naught upon 2 pi multiplied by I and multiplied by R. And this mu naught 2 pi cancels out. Value of I is 2.5. So we can say this comes as R is equal to, problem here, let me do it again, more convenient rather. Yeah, so we start from here. This will be equal to mu naught upon 4 pi and 1 plus I. This will be our 10 to the power minus 7 and I plus 1. So this is the magnetic field at, you can say, R. And now we can easily substitute the values. So Fm is given as 3.2 10 to the power minus 20, and we have magnetic field which is our 10 to the power minus 7, and here we have I plus 1, charge here 1.6 into 10 to the power minus 19, and we have this as velocity is our 4 into 10 to the power 5. And now we can just sort it out, and this gives that the value of the current will be equal to 4 amperes. That's the correct one. There was some calculating mistake on my part. And now we can just solve it. So magnetic field at So I have to correct this one also. So magnetic field will be equal to 10 to the power minus 7, and this becomes I plus 1. And I is about 4, so this comes into 5 into 10 to the power minus 7 Tesla. Now we can easily substitute. We can say magnetic field we already know. This will be equal to over 5 into 10 to the power minus 7, and we not need to find R. So this gives us that R is equal to 5 into 10 to the power minus 7, and we have here sorry yeah, so this gives us that 2 into 10 to the power minus 7 into 2.5 divided by R will be equal to 5 into 10 to the power minus 7. Now this is correct. So therefore value of R will be equal to 1 meter. So it means the third wire can be put at M or N, and we can just draw the approximate figure. So this is our P, here we have Q, and this is our R, and the velocity is in charge electron is in positive x-axis. So we are going to have magnetic field because of P and magnetic field because of Q. Therefore we have our M and we have our N, and this is suppose R, and that will be at a distance of 1 meter. Sorry for all the mistakes. So this completes our B part also, and now we come to the next question. And in the next question we are asked that it is asked in 1989, which says that a pair of stationary and infinitely long bent wires are placed in xy plane as shown in the figure. The wires carry a current of 10 ampere each as shown. The segment L and M are along the x-axis. The segments P and Q are parallel to y-axis such that OS and OR is equal to 0.02 meter. Find the magnitude and direction of the induction at point O. So we are given this figure, and in this figure we have said that we have two wires, and we have two segments. We have segment L and we have segment N, and other is our segment P and segment Q, and we have to find out the magnetic field at this point O. So from the figure we can easily see that the point O lies along the segment L as well as along the segment M. So because of this, the magnetic field because of segment L and M will be equal to 0. So this is straightforward. So we can say that the magnetic field due to straight current carrying conductor along the length at a point on the conductor is 0. Therefore, you can say point O lies along the segments L and M. Therefore, magnetic field due to segment L will be equal to 0 and magnetic field because of segment M will also be equal to 0. Now we are only interested in finding out the magnetic field at O because of segment P and because of segment Q, and the current in both the are opposite to each other. One is in positive y direction and another one is in negative y direction. So you can say that magnetic field due to segments P and Q so segments P and Q are along y-axis, and we know that the magnetic field due to, you can say, semi-infinite wire is mu naught upon 4 pi multiplied by I upon R. Okay. You can say magnetic field due to semi-infinite wire at a distance R carrying a current I it is given as B is equal to mu naught 4 pi I divided by R, and we are given that the OS distance and OR distance is same, that is 0.02 meter. So we are given that our OS is equal to OR is equal to 0.02 meters. So let us find out because of because of the segment P. Magnetic field because of segment P will be equal to mu naught 4 pi I divided by OS, and we substitute the value, we get 10 to the power minus 7 into 10 divided by 0.02, and this gives us 5 into 10 to the power minus 5 Tesla. Similarly, because of segment Q, we can write 5 into 10 to the power minus 5, because everything is same, so the value of magnetic field will be same. And the net magnetic field at so we can say that since let me write it, net magnetic field that is our B will be equal to because of P and because of Q. Although the direction of the current is in opposite direction, but if we use right hand curl rule, the magnetic field because of this segment Q will be in upward direction, and similarly the magnetic field due to this I will be also in upward direction. Okay. So it will be the summation, so we get B is equal to value same, this 5.7 multiplied by 2, and this comes as, sorry, not 7 but 5. So this comes as 10 to the power minus 4 Tesla. And next we find out the, I think this one asked, magnitude as well as direction. This part was asked. Magnitude is 10 to the minus 4, and we have, you can say, in upward. Now we come to the next question. In the next question, we ask that a particle of charge Q and mass m moving under the influence of electric field E in the x direction, I unit vector, uniform magnetic field which is in k direction, that is z, follows a trajectory from P to Q as shown in the figure. The velocities at P and Q are Vi and minus 2 Vj. Which of the following statements is or are correct? So we are given this basic figure, and in this basic figure we have an electric field which is in I direction, and we have this magnetic field which is in k direction, into outward, and the initial position of the particle P is given, and this is at a distance a from the origin, and point Q is at a distance of 2a from the origin. The velocity at P is given as v, and velocity at Q is given as 2v. The direction of velocity at point P is along positive x-axis, whereas for this other part is along the negative y-axis. Okay, that's why it is minus 2vj, and this we have vi. So we are going to find out what will be the which of this option is the correct one. So in this case, we try to find out what will be the correct option in that. So we are given that the velocity is along x-axis and another velocity is along y-axis, negative y-axis. Okay. So therefore, we start with the magnetic force of the charged particle moving in a magnetic field. We say magnetic force on a charged particle moving in a magnetic field in a magnetic field B. So we can write the formula that FB will be equal to Q, and this we have V cross B, and the force is always perpendicular to the velocity of the particle. Force is perpendicular to velocity of particle. So it means the work is related to the force component along the displacement. You can say that since work done is related to force component along the displacement, and the magnetic force is always perpendicular to displacement. Therefore, the work done by the magnetic field will be equal to 0. Therefore, work done by magnetic field will be equal to 0. So it means the work done now only be dependent upon the electric field. So for that we can use work energy theorem. Work energy theorem, which states that work done will be equal to change in the kinetic energy. Okay. And in this case, only electric field is doing the work. We can say that since only electric field can do the work, we can write that work done because of the electric field is equal to change in the kinetic energy. So at P, the velocity, let us suppose that Vp is our Vi unit vector, and at Q it is given, let us suppose, is our Vq, which is our minus 2V J unit vector. So we can write kinetic energy at P will be equal to half m V square, and kinetic energy at Q will be equal to half m, and this comes as 4v square, which can be written as 2m v square. So therefore the change in kinetic energy, that is our delta kinetic energy, will be equal to kinetic energy at Q minus kinetic energy at P. 2m v square minus 1 by 2 m v square. So we get delta Ke is equal to 3 by 2 m v square. And the work done by the electric field, that is our We, is also given as QE multiplied by 2A. So both are the work done. So let me write it here. So this gives us that the work done because of the electric field is change in kinetic energy, which is equal to 3 by 2 mv square. So these two represent the same quantity, that is work done due to electric field. So we can equate them and we can say that our QE multiplied by 2A is equal to 3 by 2 mv square. And from here we can write that our electric field E will be equal to 3 by 4 mv square divided by QA. So we were supposed to find out our electric field. So option number A is the correct one. Option A is correct one. Next, we are going to find out the rate of work done by the electric field. There are two options in it. In the first case, it says the rate of work done by the electric field at P is given as 3 by 4 mvq by A, and the second case it says that it will be equal to 0. So we say that rate of work done by electric field at P, and for that we know that our electric force due to electric field, that is of Fe will be equal to QE multiplied direction I unit vector, and the velocity at P we have a velocity is equal to V I unit vector, and we can write out that the power at P will be equal to F dot V. We substitute the value and we get this as QE, and we have this as I unit vector dot V I unit vector, and this gives us, this will be equal to QE V cos of 0, so which gives us that QE V. So this is power at P. We already know the value of E, so we substitute it, we get this as QV, and here we have 3/4 mv square upon QA, and this Q cancel with Q, and we get that power at P will be equal to 3/4, and we have this mv cube upon A. Therefore, rate of work done, that is nothing but power, is our option number B is also correct. You can say option B is correct. Option B is correct. So automatically option C will be our incorrect. Now we come to that the rate of work done by both the fields at Q is equal to 0. And both the fields at Q is equal to 0. So we know that the work done because of magnetic field is 0. So we only need to find out what will the work done because of the electric field. So we say rate of work done by electric field at Q, and we already know that the velocity at Q, let us write it as VQ, is minus 2V J unit vector, but the electric field is in I direction. Okay. And our electric field is our in I direction, which is our Q E multiplied by I unit vector. So we can find out the power at Q, that is our PQ will be equal to our force due to electric field multiplied by velocity at Q, and force into is our Q. So it's not electric field, but this is a force. So this comes Q E I, and here we have minus 2 V J. So therefore we can write that power at Q will be equal to QE minus 2V, and we have cos of 90. This gives us 0. So therefore option D is correct. Option D is correct. So 3 options are correct. Only option wrong is option number C. And we have, I think, one more question. Yeah, we are given that two particles X and Y having equal charges after being accelerated through the same potential difference enters a region of uniform magnetic field and describe a circular path of radius r1 and r2. Respectively, the ratio of their mass x1 to that of x2 is. So in this case, we know that whenever a body enters a magnetic field, it goes through a circular motion, and that is going to provide a necessary centripetal force will be provided by the Lorentz force. So we say magnetic force and circular motion. Magnetic force and circular motion. We know that in uniform magnetic field, B, the Lorentz force provides the centripetal force. So we can write our QVB will be equal to mv square upon r, and r is a capital, so let me write it r. So we can say our r will be equal to mv divided by q multiplied by v. So let us find out what will be our v, and for v we can use the energy conservation. Energy conservation, the particle is accelerated through the same potential difference. So they are going to gain same kinetic energy. So we are given particle is accelerated through same potential difference therefore they gain same kinetic energy. So therefore QV Q multiplied potential V is our half m V square, which gives us V is equal to 2QV divided by m and its square root. We substitute this value of V in our R. So let us call this equation number 1, and we have equation number 2. From equation 1 and 2, equation 1 and 2, we can write that our R is equal to 2m QV divided by its square root, and this is divided by Q multiplied by V. Now we have two masses and two radii. So we can write, let us call this equation number 3. From equation 3, we can say our R1 is our 2 mass of X divided by charge potential difference square root QB, and similarly we can write our R2 is equal to 2m y QV square root Q upon B. Now simply we are going to find out the ratio. So we get R1 upon R2 is equal to this. If we find out the ratio here only, we can understand this QB will cancel, and this 2 QV cancels out, and this gives us that square root of m of x and square root of m of y. So therefore the ratio of mass of x and mass of y is equal to r1 upon r2 and its whole square. So the options that are given to us, option number C is the correct option. Option C is correct.